The night sky is full of stars, galaxies, planets, and asteroids.
Asteroid actually means star-like. Even in the very best telescopes, they look like nothing more than just points of light in the sky.
They're cosmic boulders, and there are trillions of them. From the size of a car to giants hundreds of miles across. Together, they tell the story of how we came to be. The Earth was made by asteroids. Four and a half billion years ago, the solar system is a vast cosmic whirlpool. Dust sticks together to create asteroids.
In our own solar system and in every solar system, the first objects to form, the first large rocks before planets form, are essentially asteroids.
There are no planets yet. Instead, trillions of rocks and stones swirl around the newly born sun.
It would have been a very strange place, kind of like a merry-go-round of all these objects orbiting around the sun. And there are millions of these asteroids that are just in different sizes and different shapes.
These ancient asteroids will shape the solar system and build the planet we live on.
Asteroids are so much more than just rocks in space. They're the building blocks of our very own planet.
Billions of small asteroids must clump together to make a planet. But asteroids move at thousands of miles per hour. Getting them to stick is hard.
We're here at the stock car race. See what the early solar system may have looked like.
High-speed car collisions cause damage. Parts smash off. Asteroid collisions are the same. To join together, somehow they must collide and stick. Stock cars show how this happens. They move fast, but all in the same direction. Just like the asteroids in the early solar system. When collisions happen, they're relatively gentle. Instead of smashing apart, they join together. These are planets in the making.
They're going around almost at the same speed, and they begin to stick together, and that's how planets begin to form.
Asteroids gather into rock piles, like two cars locked together. As more asteroids collide, the rock piles grow. Building whole planets this way would take billions of years. Yet the planets formed in just a few million years. How? When the rock piles reach mountain size, gravity speeds up the process.
Gravity started to become important when they were about the size of one of the Rocky Mountains, like Pikes Peak behind me. It was when they were several miles across that they had enough mass that their gravity could start to draw material in. Now, if the Earth weren't here, and it were just Pikes Peak over there a few miles away, I would very slowly start to drift toward it, faster and faster, accelerating the whole way, until I actually impacted it. The gravity would draw me in, it would pull on me, until I actually hit the mountain itself.
Large asteroids are mountains in space. The early solar system is full of them. Their gravity pulls other asteroids toward them. The larger an asteroid becomes, the more rocks it pulls in, and the faster it grows.
At that point, the events happened very quickly. It would actually draw that stuff in and grow very rapidly.
One of these early space mountains keeps on growing until there are no rocks left to pull in. It's no longer an asteroid. It's a young planet, the Earth.
All of the planets, even the Earth, they owe their existence to the fact that there were asteroids back then.
This is how all rocky planets form. Asteroids join together until there are no more left. Mercury, Venus, Earth, and Mars are all overgrown asteroids. But beyond Mars, something went wrong. No rocky planets. Instead, billions of rocks and boulders that never join together. The asteroid belt. Out here, construction came to a halt before a rocky planet could form. Because of Jupiter, the gas giant had already formed nearby.
Jupiter is humongous. It's the 800-pound gorilla. It dominates everything gravitationally.
4.5 billion years ago, Jupiter's gravity causes havoc. It flings asteroids in every direction. Giant boulders scatter from their regular orbits onto extreme, chaotic paths. The stock car race ends, and the demolition derby begins.
Once Jupiter got involved, the solar system began to look like a demolition derby. Things colliding with each other, going in all sorts of different directions.
A cosmic pileup. Rocks smash into each other from every direction. Violent, chaotic collisions. These rocks don't clump together. They shatter and create the asteroid belt. Violent collisions still rock the asteroid belt today. In 2010, the Hubble Space Telescope captured this: the aftermath of a hypervelocity collision. Asteroids can both create and destroy. If many of them come together gently, you get planets. Too much violence, and you get the asteroid belt. Billions of rocks and boulders, a graveyard for a planet that never formed. The asteroid belt is a mysterious realm, full of danger and full of promise. A new frontier just waiting to be explored. Asteroids are as diverse as planets or moons. Some are metallic, some rocky, some icy. Some even have their own moons. They come in all shapes and sizes. From boulders all the way to miniature worlds. And they're everywhere. Distant solar systems have their own asteroid belts. The star Epsilon Eridani is just 10 light years away. It has not one, but 2 asteroid belts. Another star has a belt 25 times larger than our own.
If you were actually living on a planet in that solar system, the asteroid belt would look like a much brighter than the Milky Way, a big streak across the night sky.
Asteroid belts are the scraps left over after planets have formed. so they tell us a lot about their solar system. Our asteroid belt is full of variety. Millions of strange asteroids, each with a story to tell. Yet we have barely explored it at all. That's about to change. The first mission to the asteroid belt is underway. The Dawn probe. Its goal? To explore a mysterious, distant realm.
We're going to learn more about the main belt asteroids from this one mission than we will have since we've discovered the asteroid belt in the first place.
In July 2011, Dawn arrived at its first target and sent back these pictures. Vesta is the second largest asteroid in the belt. It almost became a planet. Then Jupiter's massive gravity stunted its growth. Today, it's a miniature world.
One of the common misconceptions about the asteroid belt is that things are fairly small. But some of the largest asteroids are really more correctly thought of as minor planets. They're several hundred miles across.
Vesta even has a mountain 3 times higher than Everest. Mark Sykes is co-investigator of the mission.
It's just a real excitement because you're seeing a new world for the first time, and you know just enough to be dangerous and trying to explain what it is that you're seeing.
Vesta is like a snapshot of the infant Earth when it was just as wide as Arizona.
We're seeing perhaps what an embryonic early terrestrial planet like Earth looked like in the first few million years of its history.
The Dawn probe has already found that Vesta has an iron core like the Earth. Evidence that the Earth's core formed when the planet was still young. This stunted world offers us a window on the Earth's distant past.
We're seeing things that we didn't necessarily expect, but that's what makes it fun.
After Vesta, the Dawn mission will head into the asteroid belt's outer reaches to explore an icy, primeval world, 4 times bigger than Vesta. There, Dawn aims to settle another mystery about the Earth's past. Where did our oceans come from? The asteroid belt is ancient, violent, and remote. Hundreds of millions of miles from Earth. But not all asteroids stay in the asteroid belt. They can roam all over the solar system. The moon's surface records a violent past, a massive cosmic bombardment.
We see evidence every night when the moon comes out. What do we see? A pockmarked, barren world. Evidence that there was an intense rain of asteroids and debris that came from outer space, completely disfiguring the surface of the moon.
Millions of craters cover the moon, including the largest in the solar system, 1,500 miles across. Itself scarred by thousands of smaller craters. A storm of asteroids blasted the moon 4 billion years ago. And if that happened to the moon, it must also have happened to Earth.
The Earth is a much bigger, more massive target in space. For every one of those craters you see on the moon, you've got to imagine 50 or 60 craters here on the planet Earth.
The impacts back then must have been horrendous. Every few weeks, a gigantic object hurtling from outer space, gouging out a huge chunk of the planet Earth.
We call it the Late Heavy Bombardment. For 200 million years, fireballs rain from the sky. The impacts trigger earthquakes bigger than any in recorded history. 10,000-mile-per-hour hurricanes rip through Earth's primitive atmosphere. But asteroids also bring a new substance to Earth. Some asteroids contain ice, frozen water that melts on impact. Each asteroid brings a little more. But could asteroids really bring enough water to cover 2/3 of our planet?
One of the questions we have is, how did water get to the Earth? Because the original Earth, we think, was very hot and very dry.
NASA's Dawn probe aims to find out. The asteroid belt still contains icy asteroids to this day, in the coldest, most distant part. In 2015, Dawn will arrive at the solar system's largest asteroid, Ceres.
Ceres is 1/3 the mass of the entire asteroid belt and 4 times as large as any other known asteroid.
A lot of it looks like pure ice.
Ceres has a rocky interior and ice-rich mantle. It's far enough away from the sun, it's cold enough that it's stable.
Ceres is just 600 miles wide, yet there may be more frozen water here than all the fresh water on Earth. The Dawn mission will find out for sure. If Ceres really does hold so much ice, it could help explain why the Earth has so much water. When asteroids bombarded the Earth 4 billion years ago, massive icy bodies like Ceres could have brought vast amounts of water.
Water itself, in the form of ice, came down from the heavens to create the lush oceans of the Earth.
And not just the oceans. Clouds, rivers, glaciers may all have come from space. The Dawn mission may uncover something even more significant on Ceres. It may find an ocean underneath the ice, an inner mantle of liquid water, melted by heat from the dwarf planet's core. Life as we know it depends on water. Wherever we find water, we may find the spark of life.
If there is a liquid water ocean underneath the surface today, that begs the question of whether there could be life there.
Extraterrestrial life could have started in the asteroid belt. Ceres could be home to basic life forms, flourishing in a subsurface ocean. If asteroids like Ceres can support life, that could reveal how life started on Earth. 4 billion years ago, asteroids bombarded the young Earth. They brought water, and they may have brought life. From the asteroid belt to Earth's new oceans, primitive organisms that thrived and ultimately evolved into all the Earth's creatures. A planet that brims with life. Our earliest ancestors may have arrived from the asteroid belt.
Perhaps these little worlds could be incubators of life throughout our solar system, maybe even in other solar systems around other stars.
Asteroids may bring life to worlds throughout the universe. They may also bring death. Asteroids are crucial to life in the universe. But once life gets started, asteroids can also end it.
Asteroids really have two sides to them. They're sort of creation and destruction all wrapped up together.
Planet Earth is right in the firing line.
We've come to realize in recent years that we live in this kind of a cosmic shooting gallery.
Astronauts witness this firsthand.
When I flew on Apollo 9 and I went outside the spacecraft, it's very likely that I was hit by, a very, very small asteroid. And, it will make a hole in a spacesuit.
Most objects in the Earth's vicinity are tiny, but they move at thousands of miles per hour.
So the suits are very, very well built, the result of which is they're very heavy. But, we've never had one penetrated yet.
The Earth, too, has built-in protection from small asteroids. The atmosphere. When asteroids hit the atmosphere, they burn.
I can remember one night when we were looking down at the dark Earth, and I kept thinking I saw an occasional flash of light, but I wasn't sure. And then suddenly we're realizing, of course, we're looking at shooting stars.
Most people don't realize that on a given night, if you lie in the grass and look up at the night sky, you'll see shooting stars, many of them each hour.
Most shooting stars are the size of grains of sand. These burn up. But larger space rocks can punch right through to the ground. Here's the proof. Meteor crater in Arizona, gouged out by an asteroid just 150 feet across.
You can see the huge force that excavated this, and you can also see the layers of material that were turned over as the crater was excavated. And so some of these rocks around here are kind of upside down from where they started.
There have been millions of impacts like this in Earth's past. There will be more. Imagine a city where Meteor Crater is now.
You'd see a fireball coming through the sky very quickly. This thing is moving at 8 miles a second, and so it wouldn't take very long for it to move across the sky and strike the ground.
Heat from the fireball scorches the surface, but most damage comes after the impact.
Once it strikes the ground, this takes a few seconds to create. So very short time, very large amount of energy, and very devastating effects.
The asteroid is obliterated. A mighty shock wave generates winds 6 times more powerful than a hurricane.
You have the blast that comes out, probably for several miles, and large debris that would crush buildings and homes.
If it hit today, the asteroid from Meteor Crater would be a city killer. But the Meteor Crater asteroid was small. It was likely a fragment from a much larger asteroid.
Whatever it is that hit in Meteor Crater wasn't very big. It was probably 50 yards across, so not even as big as a football field.
There are millions of much larger asteroids. These would cause even more carnage. Country killers, and worse. Asteroids over a half-mile wide could end our civilization. Worldwide killers. We know because it happened already. There are traces everywhere.
There's evidence of giant impacts all over the world, and it's right underneath your feet. And in fact, in some places, it's pretty easy to spot.
Like here in southern Colorado.
So this layer of light-colored rock, that's the KT boundary. And it's called a boundary because it marks the boundary between two different time periods. Everything that was put down here underneath the KT boundary had dinosaurs in it. Everything above it, no dinosaurs. So it really marks that point in time when the dinosaurs went away.
The layer is rich in an element called iridium. It's rare on the Earth's surface, but common in asteroids.
So if a giant asteroid came in, smacked into the Earth, blew out dust everywhere, the iridium inside the asteroid would have settled down into a layer all over the Earth. And that's exactly what we see right here.
The clear fingerprint of an asteroid.
There must have been some perfect morning before the asteroid impact when the land of the dinosaurs was still very much as it had been for millions of years. Then there would be something sighted up in the sky, something very bright, very hot.
The asteroid is 6 miles long, big enough to devastate the planet.
The asteroid that came in and formed this layer here was very massive and was moving very fast. And so when it impacted the Earth, that energy was turned into boom, very, very big boom.
It has the force of 5 billion Hiroshima bombs. Large pieces of Earth blow out into space, then rain back down, a storm of fireballs. Wildfires rage across the globe.
In the KT boundary layer is a layer of soot. And that's an indication that there were global fires, that everything on Earth was basically on fire after this happened.
The Earth plunges into darkness. An impact winter. Mass extinction.
Basically, you can think of this as every environmental catastrophe all happening at the same time. It was an incredibly bad day for planet Earth.
A chilling reminder of the threat from space. Asteroids this big will hit us again.
We will go the way of the dinosaurs. We will be survived, most likely by the bugs, the cockroaches. They will be the ones who will inherit this Earth. But hopefully, that's going to be a long time from now.
Is mankind doomed? Or can we dodge fate? Asteroids built our world. They brought water. They killed the dinosaurs and made room for new species. But asteroids are also a threat.
We know absolutely for certain that there will be large impacts in the future. So it's not a question of if, it's only a question of when.
Large meteor impacts happen once every 60 to 100 million years. We're due for one soon, perhaps.
If we want to survive, we need to prepare. We must find the asteroids, determine if they're heading for Earth, then stop them That's not easy, but it may be possible.
Happily, there's a difference between us and dinosaurs. We have telescopes, and we can get advance notice of an impact.
Asteroids are much smaller than stars and planets. It's hard to see them coming. To track asteroids, you need a giant telescope. Like the Arecibo Observatory in Puerto Rico.
Right now, I'm on top of the largest telescope in the world, and this place may actually be our best defense against getting hit by one of these near-Earth asteroids.
The vast bowl is 1,000 feet across. And it's not only the world's biggest telescope, it's also the world's biggest radar dish.
When you think about using radar to keep track of all the airplanes that are up in the sky, well, this one is so powerful, it can actually track near-Earth objects millions of miles away.
Unlike a telescope, radar can directly measure an object's distance and reveal exactly where it is. That's perfect for tracking asteroids. In 2004, astronomers spot a stadium-sized asteroid heading toward Earth. Its name, Apophis, after the Egyptian god of destruction. The day it might hit us, April 13th, 2029. Friday the 13th.
Apophis was the first near-Earth object of the modern era that had astronomers honestly scared. There seemed to be a 1 in 30 chance of something catastrophic happening.
Arecibo springs into action against the biggest threat from space ever detected. Apophis could devastate entire countries. But the asteroid's path is still uncertain. It might hit, or it might just miss. Only Arecibo can tell us for sure.
The Arecibo telescope was able to reduce the uncertainty of Apophis by 98%. It told us that there was no chance this thing would hit us in 2029.
It will be close. Apophis will pass closer to the Earth than the Moon. Closer even than some communications satellites. We have powerful tools to detect asteroids. Someday, we'll find one that will hit the Earth. How can we protect ourselves? The obvious strategy is to destroy the asteroid before it destroys us. But that could be risky.
You don't want to blow it up because you may end up breaking it into 2 or 3 or 5 pieces, which then end up hitting all around the Earth and wiping out many, many people.
Exploding an asteroid could cause more harm than good. Better to make it miss completely. When an asteroid is headed for Earth, their future paths cross. And they'll both reach that point at the same time. Imagine the Earth is a freight train, and the asteroid is a car, both heading for a railroad crossing. If they reach that crossing at the same time, they will collide. The best way to avoid the impact is not to swerve away from the train. It's to hit the gas or the brakes.
If you can cross the tracks before the train gets there, or wait for the train to pass and then cross them, that's what we want to do with asteroids, just to make sure that the asteroid and the Earth aren't at the same place at the same time.
By simply slowing down the car, we're going to miss. That's the way to avert a collision.
But asteroids don't come with brakes. We need another way to change their speed. One approach is to use the asteroid's gravity.
For a small enough asteroid, all you need to do is park a large spacecraft next to the asteroid.
A spaceship would hover above the asteroid's surface.
You can thrust with your spacecraft to keep it from falling onto the surface of the asteroid. And so it's like a little gravity tractor, using gravity as the tow line to move the asteroid out of the way.
Over time, the gravity between them would slow down the asteroid just enough for it to miss the Earth. Asteroids could shape our future in another way. We could turn them from a deadly threat into a precious resource. Asteroids are a creative force. They build planets. They bring water. But they're also destructive.
Asteroids are both a boon and a threat. Early on, they bring the materials for life. Later on, they can destroy life.
Asteroids bring violence and death. But life may not always be in danger.
Ultimately, if life becomes intelligent enough, it can send objects out to deflect or destroy the impending asteroids.
We now have the technology to divert asteroids. That means we can treat them not as a threat, but an opportunity. We could mine them.
Many of them are just ripe for the taking in these wonderful mineral resources. And so the asteroids in some ways are literally gold mines in the sky.
They're not just gold mines. They're zinc mines, aluminum mines, platinum mines. Just one average-sized asteroid could contain minerals worth thousands of billions of dollars. But first, we have to reach the asteroids. On April 15, 2010, President Obama announced a new plan.
By 2025, we expect new spacecraft designed for long journeys to allow us to begin the first ever crewed missions beyond the moon into deep space. We'll start by sending astronauts to an asteroid for the first time in history.
Ironically, the easiest asteroids to reach are the same ones that threaten the Earth. As they pass by, a spaceship could rendezvous with the asteroid. Yet even when asteroids come so close, asteroid mining may be too good to be true.
The reason why we're not mining the asteroid belt today and letting the space program pay for itself is because of cost. It takes an enormous amount of rocket fuel and expertise to bring back an asteroid from outer space.
But perhaps we don't need to bring the minerals back to Earth. We could use the resources of asteroids to build settlements out in space.
You don't have to build a space station, it's already there. You don't need shielding because you can simply drill right into the soil and use the rocky material as shielding against radiation and micrometeorites. So in some sense, think of an asteroid as a ready-made space station.
Low gravity makes it easy to come and go. There's plenty of water and all the construction materials that colonizers could ever need.
So one day when we have colonies in the asteroid belt and we need to build cities there, that's where we're going to find valuable deposits of metals in the asteroid belt itself.
A vast band of cities in space, strung across 1 billion miles. And not just cities, but factories, to turn metal from the asteroids into spaceships.
Perhaps asteroids could actually provide the metal, the real structure to build our spacecraft. So somewhere up there between Mars and Jupiter, there may be the makings of our future spaceships.
Ultimately, asteroids may be a stepping stone by which we can one day leave the entire solar system.
Asteroids made the Earth. Perhaps they even brought life here. And in the future, asteroids could help humans escape the Earth and colonize the galaxy.
So in a way, asteroids are drawing us out into space, whether to protect ourselves or to expand where we live.
Look out at the cosmos. Billions of galaxies. Trillions upon trillions of stars. And one profound question: is anyone else out there?
We want to find another Earth. Is there a pale blue dot orbiting some star out there in the galaxy?
The search is on for worlds that could harbor life.
We're searching for our own vision of ourselves out there in space. We're searching for our heaven.
We've already discovered more than 700 planets beyond our solar system. And yet these exoplanets look nothing like our own.
Boy, were we wrong. All these solar systems that we're seeing in outer space, we find that they don't look like our solar system at all. We are the oddball. We're the freaks.
These are nightmare worlds. And the cosmos is full of them.
We're finding all different flavors of hell, all these different ways that planets can go wrong. So that's where we are right now, searching for heaven, finding hell.
These are worlds where life couldn't possibly survive. Could we really be alone? A cosmic fluke in a universe hostile to life? We may soon have the answer.
Now we have discovered hundreds of exoplanets in outer space at the rate of over 1 exoplanet a week.
In a few years, that will probably be thousands. And in the end, there could be millions or even billions of these things waiting for us to discover them.
How could all of them be planets from hell? The quest for answers starts here, 63 light years from Earth. We've discovered a planet. It's even larger than Jupiter. And it has a serious problem. Its orbit is incredibly tight. It's closer to its star than Mercury is to our sun. And 30 times closer in than the Earth. The result is a superheated hell. But there's another reason why nothing could survive here. And that's the ferocious wind. The surface is battered by a never-ending storm. We can't see these winds with our telescopes. But we know the superstorm exists. Because of this. NASA's Spitzer Space Telescope. Spitzer can see things that we can't. It doesn't use visible light. Instead, it sees in infrared. It's a part of the light spectrum we don't see with our eyes. Infrared is heat.
One advantage of studying the universe in the infrared is it gives us this opportunity to see the light coming from planets around other stars. When you try to look at the light of a planet next to the light of a star, the star is hundreds of thousands of times brighter than that planet, which renders the planet very, very faint. But if we push into the infrared part of the spectrum, the internal heat of the planet, just as my internal heat, causes the planet to glow. Now it's observable and measurable.
Spitzer gives us something completely new. The very first weather map of a planet beyond our solar system. This simple image is a technological triumph. The colors represent temperature differences. But the map also proves the planet has hellish winds. That's because the hotspot isn't where it should be. One side of the planet permanently faces the star, so its center should be the hottest point on the planet. It isn't. Something pushes the planet's hotspot to the side. And that takes incredible force. Only a non-stop 6,000-mile-an-hour hurricane could be this powerful. "20 times stronger than the strongest winds on Earth. 8 times the speed of sound. A small shift on a weather map. Evidence of supersonic winds raging on an alien planet. Truly, a planet from hell. We're finding new planets at a staggering rate, an average of 1 a week. Each one could be an Earth-like heaven. But the more we explore them, the more hellish worlds we find. And some are so nightmarishly hot that they're more than uninhabitable. They shouldn't even exist. This Jupiter-sized gas planet is 256 light-years from Earth. In infrared, it shines like a star. Thousands of times brighter than Venus, the hottest planet in our solar system. It's a blistering 3,700 degrees. It's nearly impossible for a planet to get this hot. Its hellish temperature provides a clue to its appearance. Only an absolutely black object could absorb enough light from its star to reach such scorching temperatures.
If you were coming up on the night side away from the star, you would just see this blackness in front of you. Very little radiation, very little light. It would almost just look like the stars were avoiding a part of the sky.
Just as black pavement absorbs sunlight and heats up on a sunny day, the black planet roasts beside its star. We don't understand its atmospheric chemistry. There's nothing on Earth that can absorb so much light. The planet's only color comes from a scorching hotspot.
As you flew around to the day side, things would begin to glow red hot. There'd be a huge swirling storm, all red and glowing. What a hellish world.
Deep inside, clouds of titanium oxide swirl around a solid heart, 100 times heavier than Earth. Darkness visible, another world from hell. But some planets are even bigger, seemingly impossible puzzles.
Here's a mystery. Every astronomy textbook says that gigantic Jupiter-sized planets form way out in outer space where it's really cold. So why is a Jupiter-sized planet, what's it doing inside the orbit of Mercury?
Jupiter-type planets can only form far from their parent stars, out in the cold of space. A gas giant orbiting this close means these monsters can move. This is WASP 12b, a scorching vision of hell. It's so close to its star that its orbit lasts just one Earth day.
This world is so hot, it's over 4,000 degrees Fahrenheit. This is just crazy hot.
WASP 12b is one of the hottest planets in our galaxy.
We've never seen anything like this before. This certainly is one of the most violent environments in the universe.
WASP 12b is only 2 million miles from its star. Searing heat puffs up its atmosphere, giving it the density of styrofoam. In a big enough bathtub, it would float.
We actually think it's so close to its star that the gravity, the tidal effect of gravity, warps it into almost an egg shape. It's not even round, it's oblong.
Thousands of miles beneath the puffed up atmosphere lies a solid core. It's rich in carbon, and the pressures are extreme. There could be mountains of diamond and graphite, and seas of liquid tar. But WASP 12b won't last long. It orbits so closely that its star is literally tearing it apart, ripping away nearly 190 quadrillion tons of gas a year. "10 million years from now, WASP 12b will vanish. The question is, how did it get so close in the first place? This is the birth of a solar system. In the center, a new star. Around it swirls a disk of microscopic dust grains. These are planets in the making.
The dust grains collide, and every time they collide, they merge. And so they get bigger and bigger, and so they sort of grow like the dust bunnies under your bed. And you have 100,000 years or 1,000,000 years to make a very big dust bunny. And they get bigger and bigger and bigger.
Trillions of miles from the star, it's cold enough for ice to form. Ice picks up dust and gas. These gaseous clumps grow bigger and bigger over millions of years. Eventually, they become gas giants. In our solar system, the gas giants, Jupiter, Saturn, Neptune, and Uranus, all form this way. In the distant orbits we still see today. So how did WASP 12b end up so searingly close to its star? The answer? Gravity. This planet is huge, 40% more massive than Jupiter. Its immense gravity disturbs the dust disk it formed from, creating turbulence.
And so the planet creates waves in the disk, sort of density waves. And you can sort of think of them as like waves on an ocean.
The gas giant becomes a galactic surfer. Over hundreds of thousands of years, the planet rides the waves inward toward the star.
As the planet gets closer and closer to the star, it starts to feel the radiation from the star more and more, and so it heats up.
Surfing millions of miles from the cold outer reaches of the star system into the tight, scorching orbit we see today. An ice-cold world becomes a planet from hell.
Nobody had any real clue that you could form a planet 1 billion miles out from a star. It somehow moved in. That is incredible, but that's really the only explanation of how these planets got so close to their stars in the first place.
WASP 12b is bizarre, but it isn't alone. We've found many of these super hot, super close giants. We call them hot Jupiters. Battered by supersonic winds, blacker than night, hotter than hell. But these hot Jupiters all have one thing in common. There's no life here.
So these planets are just about as different from the Earth as you can possibly imagine.
In fact, we've now found over 100 of these things, rendering them so common that the question really emerges, which ones are the weirdos, them or us?
This planetary roller coaster has consequences. As they spiral inward, hot Jupiters cause chaos. They create a whole new class of planets from hell. Orphan worlds flung away from their star into the emptiness of interstellar space. Planets orbit stars. Between the stars is a vast sea of darkness.
We've always thought of space as being empty. That would be considered its defining characteristic. That's why we call it space.
But when planet hunters switched from gazing at stars to staring deep into space, they made an amazing discovery. Out of the darkness, between the stars, planets began to appear. First, one dark gas giant. Then several more. Eventually, 10 dark, starless planets emerged from the shadows of space.
I often wonder what it would be like to be on one of these rogue planets in between stars. The night sky would be perfectly black. It'd be festooned with stars. It'd be beautiful.
But if you were at one of these planets, you would be in a world of perpetual night. There would be no sunrise or sunset. There would be no warmth of the sun.
These planets formed around a star, but now they roam the darkness of interstellar space. Their journey here was violent, each one forced from its home orbit by the gravity of a hot Jupiter.
A Jupiter-sized planet is an 800-pound gorilla. Where does it sit? Anywhere it wants to.
Hot Jupiters are killers. As they surf in toward their star, their immense gravity disrupts the system. Hurling planets from their orbital paths.
It flings into outer space any small planet. So any planet unfortunate enough to be orbiting close to the mother star would be flung into outer space with a passing Jupiter.
These planets will never again feel the heat or see the light of a star. All the rogue planets we've found so far are gas giants, but perhaps there are smaller, rocky worlds too. Worlds that were once like Earth.
The large Jupiter-like planets are just easier to see, but there's no reason to assume there also aren't smaller orphan planets. Maybe as a Jupiter planet moves in toward the star and plays ping pong with the planets, even something like Earth could have gotten kicked out. Then you would have this cold, frozen little world, just streaking between the stars, dark and lonely.
These planets are victims of a violent gravitational battle. Frozen, orphaned Earth twins.
There may be hundreds of billions with a B of these planets roaming the galaxy. Now, there are only a couple of 100 billion stars in the galaxy, so that means these rogue planets may actually outnumber stars.
Right now, we find an average of at least one new exoplanet a week. As our technology improves, we'll see smaller and smaller planets orbiting stars, worlds with a solid surface like our own. But the first rocky planets we've found are nothing like Earth. These planets have been to hell and back. We have found hundreds of alien worlds. And now for the first time, we're finding small planets made of rock, just like Earth. planets this size are potential homes for life. But instead we find more planets from hell. Weird, nightmarish, and uninhabitable. This is Coro 7b. A world of violent extremes. Two hells in one. It's so close in that its star looms 360 times larger in the sky than our sun. On Coro 7b, the first hell is unimaginably hot. The surface is a furnace, roasting at 4,700 degrees. Lava boils, turning the atmosphere into vaporized rock. When a cooler front moves in, small pebbles condense, and rocks rain from the sky.
If that's not a classic vision of hell, I don't know what is.
But that's only half the story. The hot side of the planet is locked, permanently facing the star. Beyond is the twilight zone. It's temperate here, cool enough to turn the lava oceans into solid rock. But this pleasant zone is narrow. Travel further, and you descend into a second hell. This is the dark side. The half of the planet that never sees the sun. Eternal darkness and savage cold. The temperature is hundreds of degrees below zero.
So one side is hot, another side is cold. You either have, fire or ice in the extreme, the coldest places in the universe and the hottest places in the universe. You couldn't think of a worse place to end up.
The planet was not always this way. Turn back the clock 1.5 billion years. Coro 7b is forming. But it isn't rocky. It's a gas giant, 100 times bigger than Earth. It migrates in toward its star. As it closes in, the star blowtorches gas from the planet. Its gaseous shell blasts off into space to reveal a rocky core. Coro 7b is the skeletal remains of a hot Jupiter. Its parent star has reduced this once massive gas giant to a rocky cinder. It's hard to imagine planets more extreme than Coro 7b. Yet they do exist. Rocky worlds, machine gunned by deadly cosmic rays. This is a pulsar, 7,000 trillion miles away from Earth. It's a kind of cosmic lighthouse. This unbelievably tiny world, just 10 miles across, fires an intense beam of radiation through space as regularly as an atomic clock.
A single cubic centimeter, the size of a keyboard key, actually has about as much mass as Mount Everest. Smash a Mount Everest into a cubic centimeter, the whole star, which is only about 10 miles across, is like that.
It's one of the most hostile environments in the universe. Anything nearby gets hammered by intense gravity and magnetism. No one expected to find a planet here. But this pulsar has 3. Small, rocky, near-Earth-sized. They were the first exoplanets ever discovered, and the last place you would ever find life.
It's got a tremendous magnetic field. It's blasting out X-rays, so these poor planets are just getting cooked by radiation. The word Earth-like, I don't think could be applied to these guys at all.
The X-ray beam strafes the planets over and over, firing radiation 1,000,000 times more deadly than medical X-rays. Slowly stripping their surfaces away. These are sterile worlds.
Everybody admits there's no chance for life, at least as we know it, on the planets that orbit the pulsar.
Radiation cooks pulsar planets to death. The opposite hell is no better. Frozen worlds too cold for life. In the constellation Scorpius, 20,000 light-years away, is a red dwarf star. Red dwarfs are tiny and relatively cool. And this planet is too far away to fill what little heat there is. It's so distant, its orbit lasts 10 Earth years. It's the coldest planet we have found in the universe. Its surface is a frigid 370 degrees below zero. This is a world made entirely of ice. Methane, ammonia, and nitrogen are gases on Earth. Here they form a frozen, toxic frost. Glaciers and canyons and cliffs of ice are the only terrain. Here, hell really has frozen over. Our search for Earth's elusive twin reaches another dead end. Perhaps we are truly alone. Or will our first tantalizing glimpses of an alien world, potentially perfect for life, change everything? Earth, the only habitable world in our solar system. But in a galaxy of hundreds of billions of stars, can we really be alone? It's a question that planet hunters are trying to answer.
The whole purpose, in my opinion, of the discovery of exoplanets is to establish our true place in the universe. Who are we? Where do we belong in the cosmic scheme of things? Are there other planets that can have life just like ours?
That's where NASA's Kepler Space Telescope comes in. Kepler lets us calculate how far a planet is from its star. That's critical in figuring out whether it could sustain life. Life on Earth is only possible because we're the perfect distance from the sun, not too hot and not too cold. Just right for liquid water, oceans, rivers, lakes, rain, and life.
You know, journalists say, follow the money. Astronomers say, follow the water, because water is the universal solvent that dissolves most chemicals, and that's where DNA got off the ground. And where there's liquid water, there could be life.
We're looking for planets that are not too close to their parent star, where all the water would boil away, and not too far away from their parent star, where all the water would be tied up in a frozen form. We're looking for that Goldilocks zone, where the temperatures are just right for liquid water to pool on the surface.
Once Kepler has identified a new planet, astronomers check whether it lies in the habitable zone of its parent star. So far, Kepler hasn't found a single confirmed Earth twin. But it has identified more than 2,000 planetary possibilities. And it's this sheer abundance of planets that gives scientists hope.
The important thing to remember is that even though we're finding all of these terrible planets that are just completely unlivable, is that we're finding lots of them. We're finding hundreds and thousands of these planets. And what that's telling us is that planets are easy to make. And that means that even rare things are probably out there in large numbers. Even if the Earth is a rare, precious jewel in our galaxy, there may be dozens or hundreds of them out there.
Kepler has opened our eyes to a universe full of planets. We can now guess at how many there might be in our own galaxy. 50 billion. 50 billion worlds just waiting to be discovered. And we think 1% could be in the Goldilocks zone of their star. That's 500 million planets, each with a chance of harboring life. Right here on our own doorstep. We haven't found one yet, but we're getting closer. This is Gliese 581. A red dwarf star 20 light years from Earth.
Gliese 581 is a tiny little star. If the sun were the brightness of about a 100-watt light bulb, then Gliese 581 would be like a little Christmas tree light, a tiny little fairy light, very, very small. This shifts the life zone in, because now if you want to be warm enough, you need to snuggle up right next to the star.
The star has 4 planets. 3 are too close and hot for liquid water. But the 4th is different. It's a rocky world twice the size of Earth. And it's right on the edge of the Goldilocks zone. In theory, if the planet has a thick carbon dioxide atmosphere, it could trap enough heat to have clouds, rain, and oceans. It would be a strange place to live, twice Earth's gravity, bathed in permanent red twilight. But right now, this weird world is the closest we have to a planet like ours. It's a promising start.
When we actually know for a fact that up there around that star is a planet like Earth, that's going to just fundamentally change how people look at the sky and how people perceive their place in the universe. So that's going to be a profound moment, not just for me, but I think for humanity in general.
Our goal is to find another Earth, but along that path, we are going to find more things than we could have ever possibly imagined. And that's the part I love about this the most. We don't know what craziness is going to be around the next corner when we're looking for more planets. I can't even imagine.
Our universe, the galaxies, the solar system, our home planet Earth. Land, sea, air, life. Where did they all come from? Look up into space from our planet, and what you see is a vast cosmos, teeming with billions of stars and galaxies. Turn back the clock over 13 billion years, and our universe was a very different place. Back then it was so small that it could fit inside the palm of your hand. From this infant universe, everything would be created. Stars, galaxies, and the building blocks of life itself. The calcium in our bones, the iron in our blood, the atoms for the air we breathe, the water we drink, the raw materials for our cities and machines. Naked Science takes a journey through space and time to discover how the universe was born and how it created everything in our world and how eventually it will die. Everything we see around us is made of matter, atoms, and molecules. Take this car. It's a 1956 Ford Fairlane convertible. It's constructed from many different materials, like steel, rubber, and glass. Go deeper, and these materials are made up from combinations of elements like iron, silicon, chromium, and carbon. Each and every atom that makes up this car were created by our growing universe. Physicist Lawrence Krauss studies how the atoms we see on our planet have come to be here.
We really are part stardust and part Big Bang dust. Most of the atoms in our body are from the cores of stars, but some of them have been around since the earliest moments of the Big Bang. So we really are truly cosmic individuals.
Each and every atom was created over billions of years as our universe evolved.
So when we look at this car, of course, all the atoms in this car came from stellar explosions, from supernova processes, and from stellar evolution. But they were created at different times during the evolution of the universe.
To understand how the universe made all the raw material we see here on Earth, we need to take an incredible journey and travel back through space and time to the moment our universe was born. In the beginning, there was nothing. No space, no time. And then there was light. Suddenly, a tiny speck of light appears. It was infinitely hot. Inside this tiny fireball was all of space. This was literally the beginning of time. The cosmic clock was ticking. Time could flow, and space expand.
At the earliest moments of the Big Bang, if you take it back to t equals 0, everything in our universe, everything we can see, all the matter and all the energy in all of the galaxies was once contained in a region smaller than the size of a single atom today.
The idea that our universe was once tiny originated from the brilliant work of American astronomer Edwin Hubble. Back in the 1920s, most astronomers believed that everything visible in the night sky were stars, and they were part of our galaxy, the Milky Way. But Hubble wasn't convinced. He studied a swirling cloud of light called the Andromeda Nebula and showed that it was a star city, another galaxy, far outside of our own galaxy. He showed that these other galaxies were speeding away from ours, and the further away they were, the faster they seemed to be moving. The universe was expanding. And if the universe was expanding, then at some point in the past, it must have been smaller, much smaller. And that it must have had a beginning. The idea of the Big Bang was born. Theoretical physicist David Spergel is a Big Bang expert.
The Big Bang theory is not really a theory of how the universe began. It's really a theory of how the universe evolved.
No one knows exactly what happened during the Big Bang, but scientists do know that a fraction of a second after the universe was born, this tiny, super hot fireball was already starting to expand.
We don't know how the universe began. So we start our story when the universe was a billionth of a billionth of a billionth of a billionth of a minute old. Pretty young. The universe was the size of a marble.
Less than a trillion trillionth of a second after the Big Bang, the marble-sized universe was very unstable and underwent an enormous growth spurt.
During this period of incredibly rapid expansion, space itself was expanding faster than the speed of light.
In the same way that this hot glass ball inflates, so did the baby universe, expanding in all directions at once. And as it expanded, it cooled. A trillion trillionth of a second after the Big Bang, the universe was small enough to fit inside the palm of your hand. A tiny fraction of a second later, it was the size of Mars. Another fraction of a second, and the baby universe had grown to 80 times the size of the Earth. A trillionth of a second after the Big Bang, and our newborn universe was still expanding, but it didn't contain matter. It was pure energy. Einstein's famous equation, E equals mc squared, showed that mass and energy are interchangeable. It gave us the knowledge to build weapons of mass destruction. It also revealed how the universe created the first matter. When a nuclear bomb explodes, a tiny amount of matter is annihilated and converted into energy. In the baby universe, the exact opposite happened. It converted pure energy into particles of matter. But there was a problem. The universe created both matter and its arch-rival antimatter, and when these two met, they obliterated each other. The infant universe was a war zone, a battle to the death between matter and antimatter. If they mutually annihilated each other, the universe would remain full of energy, with no galaxies, stars, planets, or life. Fortunately for us, there was an imbalance. For every 100 million antiparticles formed, there were 100,000,001 particles of matter.
But there was that one extra particle of matter left over in each volume. And that was enough to account for everything we see in the universe today.
This tiny imbalance led to all matter we see in the universe: galaxies, stars, planets, even convertibles, and ourselves. Astrophysicist Carlos Frank from Durham University in England explains.
We are a little bit of debris left over from the annihilation of matter and antimatter. We're the leftovers of that process. If the universe had not developed this slight asymmetry between matter and antimatter, the universe would have been completely boring. There would be no structure, there would be no galaxies, there would be no planets.
Quite what this newborn universe was like has challenged cosmologists since the Big Bang was first put forward. Now, in one of the biggest laboratories on Earth, they are able to recreate conditions that almost certainly existed an instant after the Big Bang. It's called the Relativistic Heavy Ion Collider, RHIC for short, and it's located at the Brookhaven National Laboratory on Long Island. It's like a time machine, taking us back to 10 millionths of a second after the Big Bang. Here, scientists like Todd Satogata accelerate subatomic particles close to the speed of light and then smash them into each other. The particles race around this 2.5-mile circular tunnel in opposite directions 78,000 times a second, and then collide inside this giant detector bigger than a 3-story house. When they smash into each other, they generate incredible heat, just like the real infant universe.
We believe the early universe was extremely hot, billions of times hotter than the center of the sun. And what you're doing when smashing these nuclei together is melting matter, creating matter hot enough to give us a glimpse of what the very early universe was like.
When the particles collide, they break open and throw out a shower of even smaller particles. It's a bit like discovering what cars are made of by watching them smash into each other.
You can race two cars together and smash them into each other head on. And when you do that multiple times, you start to see different patterns coming out. A tire comes out here, a radiator comes out there, and before long you can start to conclude that a race car is made up of these certain pieces.
What the scientists at Brookhaven have discovered is that within these superheated collisions, a completely new form of matter appears. And this matter contradicts the previous theories on the nature of the early universe. Because it's not a gas, it's a liquid. It was super hot, 100 million times hotter than the surface of the sun. There was so much energy inside the young universe that the particles vibrated so fast that it had no stickiness. There was no friction, and it flowed perfectly.
This liquid is perfect. It has no viscosity. In some sense, it would be the perfect motor oil, except it's 1 trillion degrees hot.
Inside the collider, this amazing liquid universe exists for only a tiny fraction of a second. The Brookhaven scientists have succeeded in recreating conditions that existed over 13 billion years ago. Despite the universe being a perfect liquid, it was in turmoil. It was full of subatomic particles smashing into each other, releasing more and more energy. There was so much energy that unless the particles slowed down, they would never bond and create atoms, the building blocks of matter. And the universe would never create the galaxies and stars, or even us. The universe is now 1 millionth of a second old and has expanded from smaller than the size of an atom to 8 times the size of the solar system. After the incredible turmoil of the first millionth of a second, the universe was now relatively calm. Over the next 3 minutes, the expanding cosmos cooled sufficiently for protons and neutrons to bind together and form the first atomic nuclei, hydrogen and helium. These were not yet proper atoms. They were missing a vital ingredient, the electron. In the hot baby universe, there were plenty of electrons around, but there was still so much heat and energy the electrons were moving too fast to form bonds. And it would stay that way for over 300,000 years. 380,000 years after the Big Bang, the universe had expanded to the size of the Milky Way. It had cooled from billions of degrees Fahrenheit to a few thousand. As it cooled, the electrons slowed down. The universe was now ready to make its first true elements. One of the scientists who discovered this critical moment in the story of the universe was Arno Penzias. 1963, 30-year-old Penzias and his 27-year-old colleague Robert Wilson began work on a new antenna in New Jersey. Initially, they were only studying cosmic radio waves, but they would stumble on one of the greatest discoveries of all time. As they started to test their equipment, they detected an unexpected background noise.
It was additional signal, and it appeared to be coming from the sky. We eliminated very carefully the ground, even the solar system, because we did this winter to summer, seasonal variation, man-made sources of equipment. All these things were eliminated.
In desperation, the two scientists began to wonder whether the strange signal might have another, more earthly origin. They found there were pigeons roosting in the antenna, and it was covered with droppings. They wondered if the pigeons were the source of the strange signal. There was only one solution. The droppings and the pigeons would have to go.
We finally got around to removing the pigeon droppings. We also had to remove the pigeons. That was a difficult problem because they turned out to want to come back, and we mailed them off to another site.
But even with the troublesome pigeons gone, the mysterious signal would not disappear.
And so we were left with the almost inescapable conclusion that this radiation was coming from the sky. I could not account for it.
The strange signal detected by Penzias and Wilson would turn out to be one of the most important scientific discoveries of all time. But the explanation for their mystery background noise starts not with sound, but with the birth of light. We usually take light for granted, but in the early universe, 13 billion years ago, we would see nothing at all. Light was trapped. The universe was foggy. Imagine a flashlight beam in a fog of smoke. The light bounces back and forth between the smoke particles and is trapped. In the hot baby universe, a dense fog of electrons blocked the light from escaping. But as the universe continued to expand and cool, the electrons slowed down. Protons then grabbed these calmer electrons to form complete atoms of first hydrogen and then helium. The universe was suddenly much less crowded with electrons. The fog lifted, and light was no longer trapped. It hurtled out across the universe, creating a blinding burst of light.
Had we been there, we would have suddenly seen this opaque universe become transparent. Suddenly the fog would lift, and we would see a flash of light coming from everywhere around us. It must have been a spectacular moment.
Over time, this burst of light dimmed and cooled and became microwave radiation. It was this faint 13-billion-year-old microwave signal that Penzias and Wilson picked up on their antenna. What they heard was the quiet echo of the moment the universe formed the first atoms.
It's really the light from the origin of the universe. If you have an old FM receiver, if you tune between channels, turn the knob, and it doesn't capture it and pop to a station, you get to a part where there's none, you hear a, that's what we call noise. If you have a good radio set, 0.5% of that is actually the sound of the Big Bang.
And we can also see the moment when the first elements were created. If our television is not tuned to a station, a tiny fraction of the noise is radiation from 13 billion years ago. But this radiation is not the only reminder of the birth of the universe. Even the water we drink is a memento.
And it's kind of amazing to think that every time we take a drink of a glass of water, we're drinking in atoms that have been around since the Big Bang, the hydrogen atoms.
Over the next millions of years, the young universe continued to expand, cool, and get dark again. So far, the universe had only made hydrogen and helium atoms. But the world we live in is made from more than 100 different kinds of elements. Without them, the universe would remain a very boring place, made up of only gas, a place where complex matter, like planets, cars, and people, could never develop. The universe needed to get hydrogen and helium atoms to fuse. And to do that, it needed to make stars. The universe was now 200 million years old and billions of light years across. Its temperature had dropped so far that it was colder than liquid nitrogen, minus 367 degrees Fahrenheit. It was also dark. It would have remained a very gloomy place, full of gas, but without galaxies, stars, or planets, if it hadn't been for one thing. The baby universe wasn't born perfect. Carlos Frank has created an amazing 3D simulation of how the early universe evolved. It shows that when the universe emerged from the Big Bang, it was uneven.
Little cracks appeared, which were very, very, very tiny, very, very small. And it was this rush in the face of the baby universe that later developed into the patterns that we see in the galaxies today.
Without these cracks, the universe would have been a very dull place. The first clues as to how these cracks developed into galaxies and stars came when other scientists started to examine the Big Bang radiation first discovered by Penzias and Wilson.
So what Penzias and Wilson saw was this radiation was, as far as they can tell, uniform. What cosmologists then did for the next 25 years was work very hard to try to find tiny variations.
And find them they did, using WMAP, a space probe designed to detect and analyze in detail variations in the background microwave radiation. Launched in 2001, the $150 million probe was fitted with some of the most sensitive instruments ever carried into space. Our eyes detect only visible starlight, but WMAP can tune into the invisible microwave radiation. Once in orbit around the sun, it picked up the faint radiation that has been rippling around the universe since the dawn of time.
So when we look at the cosmic background radiation, we're looking at this radiation that's been streaming towards us since 500,000 years after the Big Bang.
Initially, the microwave universe looked very dull and seemed to be the same everywhere. But when WMAP turned up contrast, the results were spectacular. The baby universe wasn't smooth and boring at all. It was full of fluctuations.
These tiny fluctuations tell us what the variations in density, how much stuff there is, and how it varies from place to place. These denser regions are going to collapse to form clusters of galaxies and superclusters and galaxies themselves. These low-density regions, these will grow and become the empty regions between galaxies. So this picture really is our connection between the universe when it was a baby, 500,000 years old, to the universe today, 13.7 billion years old.
These tiny imperfections in the fledgling universe would become galaxies and stars.
And this is one of the most amazing propositions in physics. The idea that galaxies like a Milky Way that contain 100 million stars once began life as a tiny little crack in the fabric of the universe.
The material in these cracks was filled with swirling clouds of hydrogen atoms. The voids between the clouds grew bigger and bigger. the gas clouds got denser and hotter. Gravity pulled the gas clouds together on filaments, like beads on threads of a web, cosmic web. Where the giant filaments formed large globs, stars and galaxies would grow.
As the universe evolved, gases were able to condense into clouds, which collapse to form stars. The stars settle into a rotating disk that was later to become a spiral galaxy like the Milky Way.
Over millions of years, the hydrogen atoms clumped together and heated up. The atoms began fusing and releasing energy, and the gas clouds started to burn brightly. Eventually, a star was born. All over the universe, millions of stars ignited for the first time.
The appearance of the first stars would have been a truly spectacular event. Had we been there, we would have really seen fireworks. Individual, enormous flashes of light generated as the stars are born and burn themselves out.
The universe has expanded many trillions of times its original size. It was full of newborn stars made of hydrogen and helium. These young stars were nothing like our own sun. They were very unstable. But it was their instability that would make the universe a more interesting place, because deep inside each new star, something amazing was happening. They were creating new elements. The idea that stars build atoms came from the British astrophysicist Sir Fred Hoyle, one of the greatest astronomers of the 20th century. Hoyle didn't believe that the universe began in a single explosion. In fact, he coined the name Big Bang as a term of derision. Hoyle wanted to know where the elements heavier than hydrogen and helium came from. He figured out that stars acted like nuclear reactors, working a bit like a hydrogen bomb in slow motion. But many billion times more powerful, and their nuclear waste was new elements. But it would take years before scientists were able to confirm his theory by analyzing the light from stars. Each element emits a light at a particular frequency when heated up. Imagine a sodium street lamp. It emits light of a yellow color specific to sodium. It's the same with stars. Take our sun. If you break the light down into a spectrum, you can see lines like a barcode corresponding to the elements. Each element has specific colors, helping scientists identify elements like hydrogen, which emits mainly red light.
We are go for main engine.
In 1990, NASA launched the Hubble Space Telescope to unravel some of the mysteries of our early universe.
Liftoff of the Space Shuttle Discovery with the Hubble Space Telescope, our window on the universe.
Hubble promised scientists unprecedented views of the young universe. It would be able to look back through space and time and examine early stars to discover if they were making new elements. But the dream soon turned into the worst nightmare. After it was launched, they discovered that Hubble's mirror was distorted. It saw everything out of focus. It needed corrective lenses. And the only way to fix it was to send up another space shuttle. One of the repairmen was astronaut Jeff Hoffman.
We were working with a $2 billion telescope, and the last thing we wanted was to break something and leave it worse off than when we got up there.
First, the crew of the rescue mission had to capture the crippled telescope. Then execute a repair mission unprecedented in the history of spaceflight. First, they had to open the access doors on the side of the telescope.
The one thing about working on Hubble that is very different from working on a car is you look over your shoulder and there you are in space, and the Earth is going by below you, the stars above you.
The astronauts had to carry out fine, detailed work in the most difficult conditions.
When you're working in a spacesuit, your hands are encumbered by thick, stiff gloves. It's sort of like working in ski mittens, and it was quite a challenge.
All went well until Hoffman attempted to close the huge access doors.
I just had to close up the doors, and when I went to close them, they wouldn't close properly. The doors were somewhat warped, and it took a while for it to sink in. This was very serious. If you can't get the doors closed, you lose the telescope.
Using improvised tools, Jeff and a colleague were finally able to close the doors. It took the team 5 days to repair the stricken telescope. Cosmologists around the world held their collective breath. They waited to see if the most expensive telescope ever built would deliver what its designers originally promised.
I well remember New Year's Eve, 1993, December 31st, when my phone rang, and it was an old friend who worked at the Space Telescope Science Institute in Baltimore. He said, "Jeff, do you have any champagne left over from your party?" I said, "Yeah, we still have a half bottle in the refrigerator." He said, "Well, crack it open again and drink a glass because we got the first picture back and Hubble works."
This is what Hubble saw. The images were beyond anyone's wildest dreams. Hubble captured the final moments of a star's life when it explodes and blows off gas and dust. It also captured interstellar nurseries of newborn stars, exploding into life billions of years ago, and dark pillars of cosmic dust, millions and millions of miles long, ready to spawn a new generation of stars and planets.
I guess it's hard to surpass the famous pillars of creation in the Eagle Nebula, where you actually see the birth of stars. I mean, it's almost biblical. Let there be light. And I still kind of get goosebumps when I look at it.
But Hubble's true moment of glory was still to come. Over a 10-day period in 1995, the mission controllers pointed the telescope at a distant empty patch of space. What emerged was the Deep Field image, a tapestry of distant galaxies. Hubble was looking back in time to some of the first galaxies and stars created.
It revealed thousands of galaxies that hadn't been seen before, so the universe became, to our consciousness, far richer after the Hubble Deep Field.
It showed for the first time faint images of galaxies formed just 1 billion years after the Big Bang. Scientists then examined the spectrum of light from these distant stars and showed that these early galaxies had already created elements heavier than hydrogen and helium. Sir Fred Hoyle may have been wrong about the birth of the universe, but he was absolutely right about the stars. The early stars acted like giant thermonuclear reactors, creating new elements.
You can think of the creation of all the elements in this room as, in some sense, like a car assembly line. Because in a car assembly line, each part is sequentially added to the vehicle until it's complete.
Fusion reactions inside these young stars released enormous amounts of energy and heat, which forced atoms to fuse to form new, heavier elements, one after the other. 3 helium nuclei combined to form carbon. 2 carbon nuclei fused to form magnesium. Magnesium to form neon, and so on over a period of hundreds of thousands of years, until silicon fused to form iron. Iron is a very special atom. The protons and neutrons inside its nucleus are very tightly bound together, so that even the extreme temperatures inside the stars couldn't get it to fuse into heavier elements. It resolutely stays iron. It was the end of the road. The production line of element building shut down. But our universe was still not complete. There were all the ingredients to make a glass of water, and some of the elements to build much of our convertible. There were also quite a few of the ingredients to make a human being. The oxygen we breathe, the calcium in our bones, and the iron in our blood. But there still weren't any of the vital ingredients like chromium for our car fender. And some metals like zinc that our bodies can't survive without. The universe was about to enter a super creative phase where it produces all the elements heavier than iron. To make the missing pieces in our birth of the universe jigsaw would take some of the most powerful explosions the universe has ever seen. Our universe has already celebrated its 500 millionth birthday. There are still another 13 billion more to go before humans appear on the face of the Earth. Giant new stars have made many of the elements in the world we see around us. But some vital elements are still missing. Heavy metals like chromium and zinc, and expensive ones like gold and platinum. To finish the job, the universe conjures up the most amazing phenomena since the Big Bang. Massive exploding stars called supernovas. When the giant stars that made the lighter elements ran out of fuel, they collapsed in on themselves, creating incredible amounts of energy and enormous explosions. These explosions were so powerful, they could fuse elements even heavier than iron and restart the element production line. Tony Metzacappa from Oak Ridge National Laboratory in Tennessee believes that without exploding stars, life itself would not exist.
Life as we know it certainly would not exist were it not for core collapse supernova events. They are very clearly one of the key links in our chain of origin from the Big Bang to the present day.
One of the most recent and biggest supernovas closest to our galaxy was seen in the southern hemisphere in 1987. When a supernova like 1987A explodes, it emits light containing the signatures of the elements within it. By examining this spectrum of light, scientists can calculate what elements are being forged inside the exploding star. Michael Smith from the Experimental Astrophysics Group at Oak Ridge then recreates these events inside his own star laboratory. In this 100-foot tower, he accelerates and smashes individual particles into each other, just like inside a supernova.
These subatomic nuclei are the ones that are absolutely crucial in the formation of the heaviest elements. So the idea is to measure exactly how fast these nuclei will fuse together in the laboratory, and then translate that information into how fast they'll fuse inside exploding stars.
When the particles collide inside the accelerator, they generate enormous energy. In these extreme conditions, the particles fuse.
And then you can bring other particles in, and they will fuse. And we believe that exploding stars are just right to form elements much heavier than iron, going all the way up to the top of the periodic table.
Using the data from these experiments, Tony Metzacappa has created a model of how these massive exploding stars turn into heavy element factories.
Massive stars, they evolve to an onion-like configuration at the end of their lives. They have an iron core, and outside of the iron core are layers of successively lighter elements.
Inside the iron core, the temperature rises to 8 billion degrees, nearly 300 times hotter than the center of the sun. It is so hot that the iron atoms that have sunk to the star's core are torn apart. The core destabilizes.
The cores then collapse on themselves in a fraction of a second. The collapse proceeds to very, very high densities.
The core collapses at speeds of more than 43,000 miles per second. A volume the size of the Earth crunches down nearly 6 times the size of Manhattan in an instant. The core becomes super dense.
If one were to take 1 cubic centimeter of that matter That would be the size of a sugar cube. That sugar cube would be so dense that it would weigh as much as the entire human race.
The core rebounds like a compressed rubber ball and launches a massive shockwave. The shockwave hurtles out, smashing through the different skins of the star. As it punches through the outer layers of the star, the energy generated restarts the element production line. Atoms are smashed together to make brand new, heavier elements, all heavier than iron. Then the star explodes, and the shockwave pushes the shrapnel-like debris outward, further and further into space.
In a very real sense, our lives depend on the stars in the universe. Without their lives and deaths, we would not be here today.
These astonishing images taken by the Hubble Space Telescope show the aftermath of these giant explosions. Nebulae, giant clouds of debris thrown off by exploding stars. Swirling inside are big new atoms, gold, silver, zinc, and lead. Without supernovas, our world would be a very dull place and possibly lifeless.
So I'm sure that Paris Hilton doesn't wake up every day thinking about this fact, but really, if it weren't for exploding stars, those 200 million stars that exploded so we could be here today, she wouldn't have anything to wear. So if it weren't for those supernova explosions, there wouldn't be any bling.
9 billion years after the Big Bang, and all the ingredients are in place for life as we know it. The universe has grown up into a vast, complex place made up of billions of galaxies and uncountable stars. In a quiet corner of the Milky Way, a mass of dust and gas begins to accumulate. It's full of the rich debris left over from one of the massive supernovas. And when it reaches a critical mass, it begins to burn brightly. A star is born, our own star, the Sun. What's left over forms a disk of swirling debris in orbit around the new star. The gas and dust that make up this ring collide, pulled together by gravity. The clumps of dust and gas become bigger and bigger. Planets form. One of these planets is our Earth. Over the next 500 million years, our planet slowly generates a protective canopy of gas, the atmosphere. The first life appears, just single cells at first. But as the eons pass, those tiny single cells evolve into plants and animals, and eventually humans.
We tend to disassociate ourselves from the universe, but that, of course, is completely wrong. We are a vital part of the cosmos. And so when we talk about the origin and evolution of the universe, we're actually talking about the origin and evolution of ourselves.
Everything we can see on our planet was either made in the Big Bang or inside a star. Scientists like Krauss believe they now know the genesis of every atom that has created the world we live in.
These atoms have been around since the dawn of time. And when I was young, my mother used to tell me, "Don't touch that, you don't know where it's been." And she would have been amazed.
But this is not the final chapter in the story. After almost 14 billion years, the universe has really only just gotten started. Now we take a journey into the future to see how it all ends. The universe we live in is nearly 14 billion years old. It has created the raw materials for everything we see around us. The stars, the planets, trees, cities, automobiles, even us. Our world is complete, but the universe is still evolving. Scientists have come up with many theories on how it will end.
We know our universe began in the Big Bang. What we don't know yet is what the future of our universe is going to be. Our universe may end with a bang or a whimper or something even more exotic.
One theory suggests that our universe will run out of steam and stop expanding. Every star, galaxy, and planet, every atom will start to collapse. ending in a single super dense pinpoint known as the Big Crunch. To find out if the universe really is going to crash back in on itself, scientists first need to discover if it's still expanding or if it's slowing down. Astrophysicist Saul Perlmutter studies the death of the universe by finding beacons in space, exploding stars called Type 1a supernovas.
If you have enough of these exploding stars, these supernovae, that you've measured their brightness, so the ones that look fainter and fainter and fainter must be further and further and further away. And so you have some supernovae that are a little bit brighter, they're more nearby, some that are a little bit fainter, so they're a little bit further, and some that are very faint, so they're very far away.
Type 1a supernovas are similar to the supernovas that created the heavy elements. They differ in one important fashion. They always explode with the same exact brightness. This is because they are created in the same way. Two stars circle each other, held together by their gravitational attraction. One is shriveled and super dense, glowing with white heat, a white dwarf. The other star has bloated to an enormous size. It's a red giant that is burning the last of its fuel. As the two stars orbit each other, the white dwarf sucks gas from its companion and begins to grow year after year. When it is precisely 1.44 times the mass of our sun, the white dwarf crumples, collapses, then explodes, releasing a blinding burst of energy. Every Type 1a supernova explodes at the same tipping point, and so are equally bright and visible across the vast distances of the universe. Perlmutter needs to find hundreds of Type 1a supernovas and then measure how fast they are moving away from us. He links up the most powerful telescope on Earth with the most powerful in space. Using advanced cameras on the Hubble Space Telescope and a giant telescope officially known as the Very Large Telescope, or VLT for short, he hunts for supernovas. Once Hubble has detected a particular light source, colleague Chris Lidman at the VLT analyzes the object to see what it's made of and makes sure it's a Type 1a supernova.
This object is a distant galaxy, and next to it is what we believe is a distant supernova. The next crucial step is to understand what type of supernova this is.
The VLT breaks down the light from the object into its spectrum.
You want to be able to break up its light into a spectrum and look for the very characteristic fingerprint that you would see if it really were a Type 1a supernova.
The light emitted from this particular supernova reveals that it's a Type 1a. Lidman can now calculate how far away this supernova is.
The supernova exploded about 7 billion years ago.
By comparing the positions and dates of all these supernovas stretched over space and time, Perlmutter can calculate whether the universe is slowing down. His results are a shock. The expansion of the universe isn't slowing down at all.
When we began the project, of course, the goal was to find out how much the universe was slowing down. Now, when we actually started looking at the data, it looked like the universe wasn't slowing enough to come to a halt. And in fact, it wasn't slowing very much at all. And in fact, when we finished the analysis, it looked like it wasn't slowing, period. It was actually speeding up in its expansion.
Perlmutter's astounding discovery means that the universe will not grind to a halt, then crunch back down into a pinhead of superdense matter. Quite the opposite. It will continue to expand faster and faster. Our universe is literally flying apart.
The expansion of the universe will accelerate at ever faster and faster rates until literally everything will get ripped apart. Not just galaxies, but eventually matter, the Earth, all the objects, stars, the Earth, planets, people, atoms, in a finite time would get ripped apart.
Long after our sun has burned out, 100 billion years in the future, galaxies will pull apart. The universe will be made up of isolated stars, which are running out of energy. Some will become white or brown dwarfs. Others will collapse into neutron stars or black holes. Then, thousands of trillions of years after the Big Bang, even the black holes will evaporate, and all matter will decay to its basic ingredients. Atoms will fall apart, and even protons, the building blocks of atoms, will decay.
Most likely future is perhaps the most dismal one, where the universe becomes cold and dark and empty.
As the universe continues to expand and the galaxies speed apart from each other, space will become empty and dead.
Our own cluster of galaxies will be moving away from us faster than the speed of light and will disappear from the night skies.
Eventually, everything will just sort of wind down, and that's the end of things.
Finally, the universe will die, and all that will be left is a cold, dark, and lifeless space. The Earth. A giant mass of rock and water flying through space. It's unlike any other planet we know, because it supports life. It's not just our home. It's the only safe haven we have in the universe. But how did it get here? What strange forces of nature created this living, breathing planet we depend on? It's a mystery scientists are only now beginning to solve. Naked Science brings together the latest research to discover just what it took to create an Earth on which people could live. In this vast cosmos, there is only one place we know where humans can survive. It seems as if the Earth was made for us. It supplies us with water to drink, food to eat, and air to breathe. It's the only home we have, and we rely on it entirely. But 5 billion years ago, it did not exist. Where the Earth now sits in the outer reaches of the Milky Way galaxy, there was just a large cloud of gas and dust. This is the astonishing story of what transformed that cloud of dust into the planet we know today. One person who understands what it takes to build a planet is astronomer Tom Fleming. Using telescopes like these at Kitt Peak in southern Arizona, astronomers have pieced together how the Earth was born.
It all begins with a big cloud of gas and dust, little particles of dirty stuff, grains of sand, grains of silicon.
Scientists call these regions of dust and gas molecular clouds. But they're not like any clouds we see on Earth.
Molecular clouds are vast. They cover hundreds of light years in size.
It was from clouds like these, photographed by the Hubble Space Telescope, that the Earth formed. The clouds are made up from the debris of hundreds of dead stars. When stars from the early years of the universe burned up their fuel, they exploded and showered the surrounding space with their ashes.
When the first generation of stars died, either gently or explosively in an event we call a supernova, the heavier elements, the irons, the silicons, aluminum, nickel, that was created in the star is blown out back into the galaxy.
This cocktail of elements creates a molecular cloud. From this, new stars are born, and planets. The force that drives their creation is gravity. The same force that attracts apples to Earth will attract two objects in space toward each other. It draws the dust particles of the molecular cloud together. Over the next 10 million years, the molecular cloud slowly contracts under the force of its own gravity.
As our gas cloud collapses under the force of gravity, to become a star, something very interesting happens. And I'm going to try and demonstrate what happens with these two lead balls and this carousel. Now I'll step up here on top of the carousel. I've now increased my mass by the mass of two lead balls, and I'm holding them straight out. So now the mass in my body is distributed at a distance far from the center.
Fleming is impersonating a molecular cloud. The weights represent its mass, which to start with is spread over a huge area.
Now I'm going to ask Lucy to give me a hand here and give me a little bit of angular momentum. As I start spinning, I'm going to move the balls closer to the center of my mass, and notice how faster I'm spinning. And when I bring them out, I slow down again. And as you can see, this is exactly what happens to the interstellar cloud.
The large molecular cloud had a small rotation. When it shrank, this rotation speeded up. As the cloud contracted, the energy of the material flying in from space caused its center to heat up. This spinning ball became our sun. The rest of the cloud was spinning so fast that it spread out into a vast disk of dust and gas. This was the cradle of life, the material that would form the Earth and all the other planets. Until recently, what turned this dust into a planet was a mystery. Then, in March 2003, a lighthearted experiment on board the International Space Station led to a significant discovery. Astronaut Don Pettit was curious to see the effects of weightlessness on different substances. In a series of simple experiments, he filmed bubbles, indigestion tablets, swirls of colored water, then filled the plastic bag with salt. This last experiment turned out to be a scientific revelation. But at the time, Pettit didn't realize its significance. The person who worked out what it meant was fellow astronaut Stanley Love.
Don likes to mess with things, and one of the things he messed with was putting things in plastic bags, granular solids like sugar, salt, instant coffee. He put them in a bag, inflated the bag, and shook them up just to see what would happen. And what happened was the little particles formed up into clumps like dust bunnies instantly.
When he saw a video of the experiment, Love realized that he was witnessing a significant discovery.
And Don shot this video down. He said, "This is cool, isn't this neat?" And showed all his little videos and his different substances in the different bags. And I said, "Don, yeah, that is neat. Actually, you've solved a very old problem in planet formation."
In zero gravity, the crystals behaved completely differently to the way they behave on Earth. Love recognized what was making them stick together.
Well, anytime two different materials rub together, you can have a few electrons get traded off from one material to another. This happens when you rub a rubber balloon on your hair and stick it to the wall. As it turns out, once you get dust or basically anything in zero gravity and shake it up, let it bump into each other, we think it gets some sort of electrostatic charge on it, which makes it clump up together just immediately. You can break up the clumps by shaking the bag up, and then they reform as soon as you stop shaking it.
In the first few seconds of its life, our Earth may have looked something like this. Scientists think that this moment occurred 4.5 billion years ago. To follow the evolution of our planet, naked science is going to represent the time from then to the present as 12 hours on the face of a clock. At noon, the clock started ticking. The Earth's journey toward becoming a planet that can support life has begun. The first step didn't take long. Once clumps of these particles had grown into objects about 1/2 mile in diameter, their mass was great enough for their gravitational pull to attract material from the surrounding disk. Like giant vacuum cleaners, they circled the sun, sucking in material from the disk until there was nothing left to consume. In the inner solar system, these clumps grew into around 20 planets. This process took about 3 million years, less than 30 seconds on our clock. The next stage of the Earth's evolution was incredibly violent. As these 20 planets orbited the sun, their gravity affected each other, and they began to collide. With each collision, 2 planets combined. Over time, these collisions reduced the inner solar system to just a few planets, including Venus, Mercury, Mars, and Earth. Astronomers believe that the Earth grew to this stage in around 30 million years. We are now just 5 minutes into our story. But what was early Earth like? What would happen if a human had landed here? The energy from the collisions with other planets made the Earth incredibly hot. At around 8,500 degrees Fahrenheit, its temperature is more than 5 times that inside a cremation furnace. A human would almost instantly disappear in a puff of steam and ash. But even as our planet cools down, another danger threatens. A storm of charged particles is approaching the young Earth. It's so intense that it could end all chance of life. Four and a half billion years ago, a giant cloud of dust collapsed to form our solar system, the Sun, planets, and Earth. But as the newly formed Earth began to cool, it faced one of the biggest threats to its existence: a hurricane of deadly particles from the Sun. Boulder, Colorado. At the Space Environment Center, meteorologists monitor the storms on the Sun. It's the most extreme weather you're likely to see. A light breeze out there is 200 miles per second, and a low temperature is 8,000 degrees Fahrenheit. Around-the-clock surveillance is necessary because storms on the Sun affect us here on Earth. Space scientist Rodney Viereck knows just how deadly the Sun can be.
The Sun is a large explosion. And from that explosion, energetic particles are released.
These particles make up the solar wind, and they travel toward Earth at speeds of up to 1 million miles an hour. If the solar wind becomes too strong, it can kill.
We watch the Sun, and when we see something that may produce energetic particle events here at Earth, we try and warn astronauts, even airlines, about these types of events.
The charged particles in the solar wind are a form of radiation that can cause lethal damage to living cells. An intense solar storm could kill an astronaut caught in space. But the solar wind can also have a devastating effect on planets. The Earth is surrounded by an atmosphere, a thin layer of gases that protects it from the extreme temperatures of outer space. But when the charged particles in the solar wind hit a planet's atmosphere, they can strip it away. You can see how destructive the wind can be by looking at Mars. Over millions of years, the solar wind has blown away most of its atmosphere. Now there is no liquid water on the surface, too little air to breathe. This could have been the fate of the Earth. So why wasn't it? The answer lies in the moment of the Earth's creation. As the early Earth was forming, the energy released as material hit the planet produced heat. The heat became so intense that even rock melted. The lightest elements in the molten Earth rose to the surface, while the heaviest elements, including iron, sank down toward the center. Here, they formed a molten core. It's this iron core that protects us from the deadly effects of the sun's rays. Exactly how the Earth's core protects us is a mystery that drives the research of Dan Lathrop. In his laboratory at the University of Maryland, he spins scale models of the core to study how it behaves.
The Earth's core has dynamo action that makes a magnetic field. And that's a process where currents in the liquid iron cause magnetic fields.
Lathrop has found that the spinning motion of the core creates a magnetic shield that surrounds the Earth.
So you can see it's mostly axisymmetric, but you're getting small details that are rotating around with the inner sphere.
To show how it does this, Lathrop has rigged up a simple high school experiment.
We can see how the currents produce magnetic fields with this simple demo. Just take some iron filings and sprinkle them down around this coil of wire.
This coil of wire represents the core of the Earth. The iron filings will reveal the shape of any magnetic field.
And then hook the coil up to a power supply. You can see the iron filings line up with the magnetic field lines, and the magnetic field lines are passing through the center of the coil and looping around the ends.
The electricity in the coil produces a magnetic field. The same thing happens on a larger scale with the Earth's core. Its magnetic field gives our planet its north and south poles. It also extends far out into space. It's called the magnetosphere, and this is what protects us from the solar wind. As particles from the sun fly toward the Earth, the magnetosphere blocks their path. Those that get through are deflected toward the poles. Here, as they enter the Earth's atmosphere, they react with molecules in the air to create the aurora. The northern and southern lights. Today, the solar wind still erodes our atmosphere, but thanks to the magnetosphere, the loss is not life-threatening.
It's been estimated that between 5 and 10 pounds a second of our atmosphere are dragged out into the solar wind. Fortunately for us, even at that rate, the amount of time it would take to deplete our atmosphere would be many times the life of the sun.
The magnetic field produced by the iron in the center of the Earth played a vital role in our planet's evolution. Without it, we wouldn't have any air to breathe. On our clock, in which 12 hours represents the whole history of the Earth, just 6 minutes have passed. The Earth still doesn't look like the planet we know, but could a human now survive on its surface? It's possible that the Earth may have cooled enough for a human to survive in a heat-resistant suit. And thanks to its iron core, our planet is now protected from the solar wind. But there is still no oxygen or water on Earth. We wouldn't last a minute. Worse still, if a human could survive, they would be in for a shock. An astonishing event is about to take place. The Earth is on a collision course with another planet and about to experience the biggest bang in its history. So far, we have seen how a giant cloud of gas and dust collapsed to form our solar system, and how the Earth's molten iron core created a magnetic field that protected the planet from the deadly effects of the solar wind. The Earth's formation was a violent and dramatic process, but an even more astonishing event was about to take place. A collision so large that it would melt the whole planet. And the only reason we know this event happened is thanks to a large object circling over our heads. The moon is the Earth's constant companion. For centuries, humans wondered where it came from. There were many theories. Some thought that it was formed by the early Earth, spinning so fast that it threw off material into space. Others proposed that the moon was a passing planet captured by the Earth's gravity. But no one really knew. In 1963, the United States launched the Apollo program. One of the mission's aims was to discover how the moon was formed.
Houston, Sweet 16 has arrived. Okay. Ryan, you go for landing. Okay, down at 3. Stand by for contact. Contact. Wow! Come on, man. Fantastic.
In the late 1960s and early 70s, American astronauts made 6 visits to the moon. They played golf, tested their skills at off-road driving, and collected 840 pounds of moon rock for scientists back home to study.
How about rolling that one over? No way.
The pieces they brought back to Earth revealed something strange. When scientists examined them, they found that they were very dry, as if they had been heated. This was baffling. Any theory of the moon's creation needed to explain this mystery. In the 1990s, planetary scientist Robin Canup decided to put a new theory to the test. Using a supercomputer simulation, she modeled what would happen if the Earth collided with another planet. The results were a revelation.
This is a simulation of a single impact by a roughly Mars-sized planet, shown here in the upper right, colliding with the young proto-Earth, represented by this object here. So the impactors come in and hit the Earth at a very oblique angle, at about 45 degrees, and you can see this long arm of material right here. That's actually the impactor. It's been stretched out and distorted by the impact event itself. There's an inner clump of material, you can see it right here, that will re-impact with the Earth. after a little more time, this outer clump of impactor material. It makes a very close pass by the Earth. As a result of the Earth's gravity, this initial clump is sheared out into a long arm of material, which then finally breaks up to form a disk. And it's from this disk of material orbiting the Earth that we believe the Moon then later accumulates.
From this simulation, Canup has figured out exactly what happened during the impact.
There would have been this unbelievably large impacting planet racing towards the Earth at a speed of 7 miles per second. This would have been an enormous object, a planet that was half the size of the Earth itself, and so would have completely filled the sky just before impact. The impact itself was an incredibly energetic event with enough energy to completely melt the whole of the Earth and vaporize a significant portion of the rock in the Earth.
When the planet hit the Earth, the glancing blow smashed material into space. Much of this debris stayed in orbit as a vast disk of rock and dust. A clump of this circling material then became large enough for its gravity to suck in other matter from the disk. And this became our moon. It's now 50 million years since the Earth began to form. On our clock, in which 12 hours represents the whole of Earth history, still only 8 minutes have passed. At this stage in its life, the Earth appeared very different to the planet we know. The ground remained molten from the impact for thousands of years, and the moon was 15 times closer than it is today.
You can imagine what is now a stunning sight on a full moon night would have been breathtaking at that time, with the moon 15 times larger than we currently see it.
The collision with the planet and the formation of the moon were key events in creating an Earth fit for life. The collision could have tilted the Earth on its axis. This tilt gives us the seasons. Thanks to this tilt, the Earth's climate changes gently through the year. It gives us the annual cycle of life. It may have been possible for life to evolve on Earth without these seasons, but it would have been a very different planet from the one we know today. The creation of the moon also gave us the tides. When the moon was close, these were much stronger, but they have weakened as the moon has slowly drifted away. Nowadays, we take the oceans for granted, but 4.5 billion years ago, they didn't exist. And without water, there could be no life. Where all our water came from and how it got here is one of the most amazing stories in science. Naked Science is investigating the birth of the Earth. How did nature build a planet on which humans could live? So far, we've seen that the Earth formed from a giant cloud of gas and dust. Its iron core created a magnetic field that protected it from the deadly particles of the solar wind. And it survived a big hit from another planet. But for the Earth to have life, it had to have water. Where that came from is one of the great mysteries of science. There are currently around 326 million trillion gallons of water on the planet. That's 394 trillion Olympic swimming pools. But many astronomers think that if the early Earth contained water at all, it had very little. At the time the Earth was forming, the inner solar system was too hot for liquid water to exist. The region from the Sun to the asteroid belt was almost bone dry. The nearest water reserves to the Earth were now 160 million miles away, in the outer asteroid belt. Out here, far from the Sun's heat, water froze and was incorporated into the forming planets and other objects. But how the water could have traveled from here to the Earth is a mystery scientists are only just beginning to solve. One clue came with the blastoff in January 2005 of an unusual NASA spacecraft. Named Deep Impact, its mission was to fly 270 million miles to a comet named Tempel 1 and launch an 800-pound copper impactor into its surface. The mission was the latest attempt to understand some of the most mysterious objects in our solar system. For centuries, people had argued that comets had brought water to Earth. When they looked at the moon, it was clear from the craters that its surface had been bombarded by large objects. Similar objects must also have hit the Earth, although our planet's much more dynamic geological activity has since erased all trace of them. Scientists also felt certain that comets contained water in the form of ice. But the Deep Impact mission was the first time anyone had probed inside one. On the morning of July 4th, 2005, NASA scientists waited anxiously as the impactor approached the comet at a speed of 23,000 miles per hour. It scored a direct hit. The explosion was captured by telescopes around the world. Analysis of the debris confirmed that comets contain significant amounts of water. But could they have brought that water to Earth? Using radio telescopes, astronomers have studied the type of water in the vapor trails of comets. They wanted to know if it matched the water on Earth. So far, scientists have only analyzed 3 comets, but the results are not encouraging for the comet theory. The water in all these comets was not the same as the water in our oceans. The comet theory isn't yet dead, but it's fizzling out of steam. In its place, scientists have evolved an exciting new idea. A vital clue arrived on January 18th, 2000. That evening, the sky above Western Canada lit up with a bright light. Dozens of witnesses saw a meteorite enter the Earth's atmosphere. Seconds after the event, local photographers took these pictures of the trail it left in the sky. As it fell to Earth, the meteor broke up into dozens of pieces and landed on Tagish Lake in British Columbia. Within days, scientists were on the scene extracting the frozen remains. The pieces they pulled from the ice were the best preserved meteorites ever recovered. Still intact, a piece was shipped to NASA's laboratories at the Johnson Space Center in Houston. Here, space scientist Michael Zelensky examined it. The meteorite was remarkably undamaged, despite heating up through friction as it entered the Earth's atmosphere.
The meteorites, they're cold soaked in space for millions of years. So they're very, very cold. And they enter the atmosphere at high velocity, and they do in fact get very hot on the outside, but they're only heated for a few seconds. And that's not long enough for the heat to get all the way in past a few millimeters, actually.
This means that when meteorites hit the ground, they cool very quickly.
You hear of reports of meteorites causing fires on the ground, things like that. That's always wrong. They're actually quite cold to the touch after a few seconds.
But when a meteorite is fragile, like the one at Tagish Lake, where it lands makes all the difference.
We're lucky it fell in a frozen lake. If it had fallen anywhere else, it would have easily fallen apart to dust in a few days. And so it's quite possible this kind of meteorite falls to Earth very, very commonly. It's just usually destroyed.
Because the inside of the meteorite remained frozen, Zelensky was able to analyze what it was made of.
This is a sample of the Tagish Lake meteorite. The black material here is mostly clay minerals, the kind that you'd find in your yard, and these clay minerals contain water molecules trapped inside. And so about 20% of this meteorite by weight is water. That's a huge amount.
From the location and angle at which the meteorite fell, astronomers traced its orbit back into space. They discovered that it came from the outer reaches of the asteroid belt.
If you do telescopic observations of asteroids, what you find is, as you move farther and farther from the sun, the asteroids have more and more water.
Now, astronomers suspect that asteroids from this outer part of the belt brought water to Earth. If they're right, our oceans came from space in a torrential shower of meteorites. But one question remains. What could have caused so many asteroids to swing out of their orbit and come crashing to Earth? The culprit appears to be the biggest planet in the solar system. Jupiter lies just beyond the asteroid belt, and its mass is so great that its gravity disrupts the path of any object it comes near. In the distant past, it pulled thousands of asteroids out of their normal circular orbits into elliptical orbits that crossed the path of the Earth. When that happened, collisions were inevitable. The Earth was bombarded. As the asteroids crashed to Earth, they smashed apart. Water inside them escaped. Explosion by explosion, they created the oceans we see today. Scientists used to think it took hundreds of millions of years for the Earth to acquire its water, but recent evidence suggests it arrived remarkably quickly. The evidence comes from research carried out by geologist Stephen Moisish. In his laboratory in Boulder, Colorado, Moisish took some of the oldest rocks in the world and ground them down. From inside them, he extracted tiny crystals called zircons.
Zircon is a common mineral. It's generally small. It's hard to destroy.
Using an ion microprobe, Moisish then analyzed the zircons and measured the composition of the oxygen inside them. He found that the crystals had formed from a particular type of rock, one that could only have existed if there was water on Earth.
What was startling, exciting, fun was that these zircons showed not only that things on the Earth's surface had stabilized to within normal conditions, but that water was present, and water was present everywhere.
Moisish estimated the time the Earth acquired its water from the age of the zircons.
The zircons in some of the rocks there are very close to 4.4 billion years old.
This evidence suggests that the Earth's water arrived in less than 150 million years. On our clock, on which 12 hours represents the whole history of the Earth, that's just 25 minutes after the planet began to form. At this time, our Earth would certainly have looked very different. The sea was full of iron, much of it brought up from below by hydrothermal vents, and the atmosphere was a lot thicker than it is today.
An ocean rich in iron would have appeared green. A denser atmosphere would have given a reddish tinge to the sky.
Conditions for human existence are looking better. The land has now cooled to a tolerable temperature, and there is water to sustain life. But there is still one horrendous problem. The gases in the atmosphere are mainly nitrogen, carbon dioxide, and methane. There's not a lungful of oxygen in sight. Without oxygen to breathe, there's no way a human could survive. In the early years of its life, the Earth experienced a violent and tempestuous onslaught. In time, the activity slowed until 500 million years after it began to form, the Earth had cooled and was covered in oceans. But there was still no oxygen in the atmosphere. Without that, animals and humans could not exist. One scientist who has investigated how the Earth acquired its oxygen is geologist Martin van Kranendonk. His research has brought him to Shark Bay on the west coast of Australia. It's a World Heritage Site, home to vast meadows of seagrass, dugongs, and tame dolphins. But Van Kranendonk has come to visit much older living things. This is one of only 2 places in the world where these strange living structures, called stromatolites, are known to exist.
These stromatolites have been growing here since the end of the last ice age, about 10,000 years ago. And at that time, the sea level was a little bit higher. And so these structures grew up to the present height that you see them.
Stromatolites are primitive structures. Here they come in 2 forms: short pillars of living bacteria and silt, and flat bacterial mats. The living part of the stromatolite is made up of blue-green bacteria that grow using photosynthesis. They take energy from the sun and convert carbon dioxide into oxygen.
It's really the result of this process of giving off oxygen that we have planet Earth as we know it today, and habitats that people like us, humans, and all the other animals and plants are able to live on planet Earth.
What makes Van Kranendonk believe that stromatolites created the Earth's oxygen is a remarkable discovery 1,000 miles away in a remote region of North Australia. This is the Pilbara, one of the oldest landscapes in the world. If you want to find out what happened early in the Earth's history, this is the place to come.
It's really like you're transported back into a time machine of early Earth. It just sort of gave me goosebumps and shivers to walk over this ancient environment where you could still see the processes that happened 3.5 billion years ago.
Here, at a location kept secret to preserve them, lie the oldest fossils ever discovered. The ancestors of the stromatolites in Shark Bay.
What's remarkable about this outcrop in the Pilbara is that it contains the oldest evidence for life on Earth. We're looking at here in front of me our great-great-great-great-great-great-great-grandfathers and grandmothers.
No one knows how life on Earth began, but these amazing fossils suggest that it emerged very soon after the planet formed. These fossil stromatolites are 15 times older than the dinosaurs. The bacteria that made them were living here just 1 billion years after the birth of the Earth. On our 12-hour clock, the time is now 20 minutes to 3.
These would have been the first organisms that would have started the process of change of Earth's atmosphere to an oxygen-rich atmosphere, which has allowed us, mankind, and all the rest of life that we know today to evolve on planet Earth.
If stromatolites existed on the Earth 3.5 billion years ago, they should have started to increase the amount of oxygen in the air. But it appears that they didn't. For the next billion years, the oxygen level in the atmosphere hardly changed. What happened to all the oxygen the stromatolites produced can be seen 300 miles away in this gorge in Australia's Karijini National Park. Hidden in these rocks lies the key to the mystery of the missing oxygen. Geologists call these rocks banded iron formations, and they believe that they owe their existence to stromatolites.
Well, these banded iron formations are the product of a remarkable set of circumstances in Earth history. They formed about 2.5 billion years ago when the Earth was very young, and are the product, we think now, of microbial action in the ancient oceans.
The Earth's early oceans were full of iron. As the bacteria in stromatolites bubbled out oxygen, it reacted with the iron in the water. You can see what happened in this simple experiment. This flask of water contains iron. It's the same color as the early oceans on Earth. This pump does the work of a stromatolite pumping out oxygen. As the oxygen bubbles through the water, it reacts with the iron to form iron oxide, and it precipitates out as rust. There was so much iron in the oceans that for over 1 billion years, it absorbed nearly all the oxygen that the stromatolites produced. As the rust precipitated out, it fell to the bottom of the ocean and was turned into rock. It has been estimated that around the world, these rocks have locked inside them more than 20 times the amount of oxygen that is in the atmosphere today. And they took an incredibly long time to form. On our clock, in which the whole history of the Earth is represented as 12 hours, we can see that the planet forms in the first 8 minutes. After 25 minutes, it has cooled and collected water on its surface. But it takes another 4.5 hours to remove most of the iron from the oceans and deposit it in these rocks. Only then does the oxygen level in the atmosphere start to increase. This happened approximately 2.5 billion years ago. And for the next 2 billion years, the level rose. Until just 500 million years ago, it reached the level at which animals could survive. So is our planet finally fit for human life? By this time, it has certainly cooled. There is water to drink and air to breathe. If we could travel back to this time, we could certainly survive. In our story, 11 hours have now passed. But the Earth still has a long way to go before the first humans will walk on its surface. At 37 minutes to midnight, dinosaurs will emerge. At 10 minutes to midnight, they will be wiped out by a catastrophe. Finally, at 19 seconds to midnight, the first humans will appear. It has taken over 4 billion years, but out of a vast region of freezing dust and gas, the forces of nature have created the only safe haven we have in the universe. Our home, the Earth.